Hi folks, welcome to this chapter, Mass Stoichiometry. In this chapter, we are going to be looking at mole conversions, molar mass, percent composition, stoichiometry, theoretical yield, and percent yield. The masses of elements and compounds play a very important role in chemistry. Chemists use mass to identify unknown compounds and to understand and predict chemical reactions. As we saw in chapter 3, the periodic table shows the average mass for atoms for each element. For example, here for hydrogen, it shows the average mass of atoms of hydrogen. For carbon, it shows the average mass, and for oxygen, the same. Now, when working with compounds, we use these atomic masses to calculate the mass of a single formula unit. This is called the formula mass. So, for example, what is the formula mass of water? Now, before we go into calculating the formula mass of water, I want to stress how important masses are to chemists. So, let's say some chemists are working with plants, medicinal plants, and they discover that there is a particular plant that is used to treat a particular illness. Now, chemists are going to use the mass of that compound to determine the structure of that compound and subsequently the formula. So they use an analytical technique that is called mass spectrometry to determine the mass of that compound after isolating the active ingredient in that plant. They will now use mass spectrometry, and from the mass spectrometry, they will use other analytical techniques like the nuclear magnetic resonance to determine the structure and the bonding of the atoms. Now, let's get back to our example. What is the formula mass of a water molecule? Let's state again what is formula mass. Formula mass is the mass of a single molecule or a formula unit. Now, for a water molecule, for us to be able to calculate the formula mass, we must first of all write the formula of water. So the formula of water is H2O. Now, in water, we have 2 hydrogen atoms and 1 oxygen atom. For us to calculate the formula mass, we are going to take the number of each atom and multiply by the mass. So we have 2 hydrogens. We are going to multiply by the mass of hydrogen. So that gives us 2 times 1.01 atomic mass units, plus the mass of oxygen is 16.00, and we have 1 in water. So that is going to give us 1 times 16.00. That gives us an answer of 18.02 atomic mass units. So when you see U or AMU, that stands for atomic mass units, and it is a unit of measuring mass, atomic mass units. So we can also call the formula mass, chemists sometimes call it the formula weight, they sometimes call it the molecular mass, and they sometimes call it the molecular weight. So when you hear of formula mass, formula weight, molecular mass, or molecular weight, they often refer to the same thing. Now, let's determine the formula mass of a compound here, potassium carbonate. Potassium carbonate is a common water softening agent. What is the formula mass of this compound? We have to first of all write out the formula of that compound. And we see that in this compound, we have 2 potassium atoms, 1 carbon atom, and 3 oxygen atoms. So to calculate the formula mass of this compound, we are going to take 2 times the mass of potassium, which is 39.10, plus 1 times the mass of carbon, which is 12.10, plus 3 times the mass of oxygen, which is 16. So 3 times 16. And we sum all of that, which is going to give us the formula mass of potassium carbonate. So let's go ahead and do it. So 2 times 39.10 atomic mass units plus 1 times 12 plus 3 times 16. That gives us 138.21 atomic mass units. So that is the formula mass for potassium carbonate. Now, let's look at what we call percent composition. So when we talk of percent composition, let's go back to the example we've just seen, potassium carbonate. If you are asked to calculate the percent composition of potassium in potassium carbonate, it means that you are going to take the mass of potassium in this compound divided by the total mass of the compound times 100. That is what is called percent composition. So percent composition of one element is equal to the mass of one element divided by the mass of the compound times 100. Now let's look at an example here. Octane, a compound of gasoline, has the molecular formula CH18. What is the percent composition of carbon and hydrogen in octane? Now, for us to be able to calculate the percent composition of carbon and hydrogen in octane, we have to first of all start by calculating the mass of carbon in this compound and the mass of hydrogen in this compound. Then we sum all of them to have the total mass of the compound. Then, for the percent composition of carbon, we are going to take the mass of carbon over the mass of the compound times 100. And we are going to do the same thing for hydrogen. Now let's start with carbon. So the mass of carbon will be 8 times 12.01, because the mass of carbon is 12.01 and we have 8 of them. So that gives us 96.08. Now for hydrogen, we know that the mass of hydrogen is 1.01 and we have 18 of them. So the mass of hydrogen is 18 times 1.01, and that gives us 18.18 atomic mass units. Now, the next step will be to calculate the total mass of the compound. So it will be the sum of these two. So let's sum all of them. The mass of the compound will be 8 times 12.01 atomic mass units plus 18 times 1.01 atomic mass units. And that gives us a mass of 114.26 atomic mass units. Now, to determine the percent composition by mass for carbon, we are going to take the mass of carbon divided by the total formula mass times 100. And we have calculated the mass of carbon here to be 96.08. So we have 96.08 over the total mass. The total mass is 114.26 times 100. So the mass composition, the percent composition of carbon is 84.09. Now let's look at the percent composition of hydrogen. Now, the percent composition of hydrogen will be given by the mass of hydrogen over the total formula mass times 100. So we've calculated the mass of hydrogen and we have 18.18 atomic mass units. And the total mass of the compound is 114.26. So the percent composition of hydrogen will be 18.18 atomic mass units over 114.26 atomic mass units times 100, and that gives us 15.97%. Now, let's look at what is called the mole concept. We've been working with atomic mass units. I've been mentioning atomic mass units to you. Now let's see what exactly is the atomic mass unit. One atomic mass unit is equivalent to 1.66 times 10 to the minus 24 grams. So this is a very small amount in terms of grams, very small. So we did how we can convert units, and we looked at the power raised to the 10. So we looked at that, and if you look at this this measurement here, it is a very small value. So how do we relate the atomic mass to larger amounts? Because this is a very small amount. Okay, how do we now relate it to larger amounts, like the amounts that chemists can use in the laboratory or in factories? Because you cannot measure out 1.66 times 10 to the minus 24 grams. That is very difficult. So for chemists to solve this problem, they are going to use what we call the mole. Now, we know that when we hear of a dozen is equivalent to 12 units. So when they talk of a dozen of planets, we mean 12 planets. When we talk of a dozen of toothpicks, we mean 12 toothpicks. When we talk of a dozen of donuts, we mean 12 donuts. Now, when we talk of a mole, one mole is equivalent to 6.02 times 10 to the 23 units. So as you hear of a dozen equal to 12, a mole is equal to 6.02 times 10 to the 23 units. So when you hear of a mole of donuts, it is equal to 6.02 times 10 to the 23 donuts. And a mole of carbon atoms is 6.02 times 10 to the 23 carbon atoms. A mole of oxygen molecules is equal to 6.02 times 10 to the 23 oxygen molecules. Now, this 6.02 times 10 to the 23 is what is called in chemistry the Avogadro's number. So the mole is referred to as the Avogadro's number. Now, let's see how we can relate moles of atoms to grams. So the moles help us to relate atoms to grams, because we were talking of atomic mass units. We are talking of atoms, but we cannot measure atoms in the lab. But what we can measure in the lab, we can measure grams. So the mole helps us to relate atoms to grams. So 1 atom of carbon is equal to 12.01 atomic mass units, and 1 mole of carbon is equal to 12.01 grams. So the mole helps us to relate atoms to grams. Now, let's see here. So the mass of carbon, 12.01 atomic mass units and 12.01 grams per mole. So we have 12.01 grams per mole of carbon. So we call this the molar mass of carbon. So let's see how we can actually relate the atoms to grams. What is the formula mass of carbon dioxide? So let's go ahead and calculate the formula mass of carbon dioxide. So the first thing that we have to do, we write the formula of carbon dioxide. And in carbon dioxide, we know that there is 1 atom of carbon and there are 2 atoms of oxygen. So we are going to take 12.01 times 1 plus 16 times 2. That gives us 14.01 atomic mass units. So 1 molecule of carbon dioxide will give us 44.01 atomic mass units. Now, 1 mole of carbon dioxide gives us 44.01 grams. So the molar mass of carbon dioxide will be 44.01 grams per mole. Now let's see how we can convert between grams and moles. This is very important. Please follow as we move. Now, to convert between grams and moles, we are going to use the molar mass as a conversion factor. So the first thing, make sure you understand how to calculate the molar mass. We have been calculating the molar masses all along. I've just showed you how to calculate the molar mass of carbon dioxide here. We've also calculated the molar mass of potassium carbonate. We also calculated the molar mass of water. So we are going to be using the molar mass to convert from grams to moles. Now, how many moles of sodium chloride are present in a 305 gram sample? So the first thing that you have to do here is that you should be able to calculate the molar mass of sodium chloride. Now, when you have calculated the molar mass of sodium chloride, we are now going to use the molar mass as a conversion factor to convert from grams to moles. So, as always, like we were working with a dimensional analysis, we always start with the amount that is given to us here. So we are going to start with 305 grams. So the formula mass of sodium chloride is 58.44 grams per mole. So you can calculate that using the periodic table. Now, it means that the conversion factor here, what we are going to use, we can use 1 mole is equal to 58.44 grams, or we use 58.44 grams is equivalent to 1 mole. So this is the same thing. Now, let me call this A and B. Depending on what we are looking for, we are going to decide which of these conversion factors that we are going to use. Here in this our question, we've been given 305 grams of sodium chloride. So we have to use the conversion factor in which the grams are going to cancel out. Okay, so here we are going to use this conversion factor because grams is found at the bottom and the grams will cancel out with the grams that is found at the top. So that is the conversion factor that we are going to use to convert to moles. So we are going to multiply that by 1 mole equivalent to 58.44 grams. So what happens? We see that the grams of sodium chloride cancels out with grams of sodium chloride. So we now have moles of sodium chloride. So we've been asked how many moles of sodium chloride. So that just now gives us 5.22 moles of sodium chloride. Now, if you use the other conversion factor B, you are going to have a wrong answer because you will have different units and not moles. So make sure you know which conversion factor you are using. Now, let's see another example here. To prepare a solution that contains 1.20 moles of sodium chloride, how many grams of sodium chloride are needed? Okay, now in this case, we still have to calculate the molar mass of sodium chloride. Now we'll be converting from moles to grams. In this first case, we're converting from grams to moles. Now we are converting from moles to grams. So we know that 1 mole of sodium chloride is equal to 58.44 grams, or 58.44 grams is equal to 1 mole. So this is the conversion factor. Based on the question that we are given, we will decide which of those conversion factors to use. Here, we have been given our question in moles. So we are using the factor, the conversion factor where moles is at the bottom so that it will cancel with the moles at the top. So this is what we'll be using now. So 1.20 moles of sodium chloride, we are going to multiply that by that conversion factor. So we'll have grams at the top and moles at the bottom. So we see that when we express it this way, the moles of sodium chloride will cancel with the moles of sodium chloride and we are left with grams. So if you multiply that out, you are going to have 70.1 grams of sodium chloride. So in these two examples, we have converted from grams to moles and we have also converted from moles to grams. Make sure you understand how that functions. Now, let's now see how we can convert between moles and particles. So, for us to be able to convert between moles and particles, we are going to use the Avogadro's number. And the Avogadro's number is 6.02 times 10 to the 23 particles or ions or atoms. So, it's equivalent to 1 mole. Now, let's see an example. How many atoms are in 4.20 moles of gold? Now, to calculate the number of atoms in 4.20 moles of gold, we must use the Avogadro's number. Okay, now let's see the conversion factor. We know that 1 mole is equivalent to 6.02 times 10 to the 23, or 6.02 times 10 to the 23 is equivalent to 1 mole. So, as we always start with what we are given, and we use the conversion factor that will cancel out with the units and give us what we need. So, we have it here in moles at the top. So, we are going to use the conversion factor where moles will be at the bottom. So, this is what we are going to use. So, we have 4.20 moles of gold times 6.023 times 10 to the 23 atoms over 1 mole. So we see that moles will cancel with moles and we are left with atoms. So we are asked how many atoms. So we are just going to multiply 4.20 times 6.02 times 10 to the 23, and that gives us 2.54 times 10 to the 24 atoms of gold. Now, let's see how we can relate atoms to grams. For us to relate atoms to grams, we have to use the Avogadro convert it to moles and then to grams. So what is the mass in grams of 2.54 times 10 to the 23 iron atoms? So we are going to use the Avogadro's number here. So the conversion factor, as we know, 6.02 times 10 to the 23 is equal to 1 mole, or 1 mole is equal to 6.02 times 10 to the 23. So here we are given ions, we are given atoms. So we have to put the 6.023 times 10 to the 23 at the bottom. So this will be at the bottom so that the atoms cancels out and we are left with moles. So let's start with what we are given. We are converting from grams to moles and then from moles to atoms. So we have, for 1 atom of iron, we have 55.85 grams. So the molar mass of iron is 55.85 grams per mole. Now, we know the Avogadro's number as we've stated, so we are going to use this conversion factor to carry out that calculation. So we start with whatever we are given. This is what we are given. And now we are going to multiply by that conversion factor. The conversion factor here is the one where the 6.023 times 10 to the 23 atoms will be at the bottom, so that the atoms will cancel out with the atoms. So that is what we have. And the atoms cancel with the atoms and we are left with moles. Now, we have moles of iron. But what have we been asked? What is the mass in grams? So we are now going to apply what we already know. To convert from moles to grams, we are going to use the molar mass. So we are now going to use the molar mass of iron, which is 55.85 grams per mole, to convert these moles to grams. So we see here now that moles of iron will cancel with moles of iron, and we are left just with grams of iron. So if you carry out this multiplication and division, that gives you 23.5 grams of iron. Now, this is what you should know. To convert from grams to atoms, you first of all have to convert from grams to moles using the molar mass, and then you convert from moles to atoms using the Avogadro's number. So this is very important to understand. Now, let's see now how we can use the mole concept in balanced chemical equations. We've been using the mole concept just in simple systems, like just calculating like we just did for iron, carbon dioxide, and the others. Now let's see how we can use it in balanced chemical equations. So in balanced chemical equations, we can actually use the moles of one of the reactants to determine the mole of the other reactants, and equally the moles of the products. So this is what is called stoichiometry. So we are going to use stoichiometric coefficients in a balanced chemical equation to determine the moles of the other reactants or products. So that is why we first did balancing chemical equations, because if you have to calculate the coefficients and you don't have a balanced chemical equation, you will fail the question automatically. Now let's look at this equation that we have here. This is an explosive reaction where hydrogen reacts with oxygen to form water. So this reaction can actually be read in two ways. Now the balanced equation shows that 2 moles, we are looking at it in two ways. The first way, we are going to state it this way. In the molecular ratio, we say 2 molecules of hydrogen react with 1 molecule of oxygen to form 2 molecules of water. We are looking at it in terms of molecules. Now, we can also look at it in this second way in terms of moles. Now, when we look at it in terms of moles, we will say that 2 moles of hydrogen reacts with 1 mole of oxygen to give us 2 moles of water. This is very important. The balanced chemical equation is your first asset. If you don't have that, you are going to fail. Now, let's see how we can use the mole concept here. If 235 grams of iron react in this way, so this is the balanced equation, iron, 1 mole of iron reacting with 2 moles of hydrochloric acid to give us 1 mole of iron 2 chloride plus 1 mole of hydrogen gas. So in the balanced equation, we have the mole ratios, and we are going to be using the mole ratios to calculate the moles of other species in this reaction. Remember here we've been given 235 grams of iron. So we are going to use this 235 grams of iron to calculate the grams of hydrochloric acid or the grams of iron chloride or the grams of hydrogen. So that is what is called stoichiometry, using the grams of one species to calculate the grams of the other species in a balanced chemical equation. Now let's go ahead. Here are the questions that you've been asked. How many moles of iron react if you are given 235 grams of iron? Using that balanced equation, how many grams of iron, how many moles of iron react? The second question, how many moles of iron 2 chloride are formed? So I'm looking at this question. This is the first, this is the second, this is the third. Now the third question, how many moles of hydrochloric acid are needed? And the last question, how many grams of iron 2 chloride are formed? So let's start with the very first question. How many moles of iron react? Now, to know the moles of iron that have reacted, we need the molar mass of iron to calculate the number of moles. So we've already seen a couple of examples using that. So let's start with that case. So the molar mass of iron is 55.85 grams per mole. Now, we are going to start with the mass that we've been given, 235 grams of iron. So we are using the conversion factor here, which is the molar mass. So we'll state it in a way that the grams will be at the bottom and the mole will be at the top. So the conversion factor that we are using here, so let me show you this. We have 55.85 grams per mole. We also have 1 mole to be equivalent to 55.85 grams. So which of these conversion factors are we going to use? We are going to use the conversion factor that has the grams at the bottom so that they cancel out with the grams in the question that we are given. So we are going to write out our 235 grams of iron times the conversion factor, 1 mole divided by 55.85 grams. So we see that the grams will cancel with the grams of iron and we are left with moles of iron. That gives us 4.21 moles of iron. So now the next question is, so now let's write out 4.21 moles of iron. Now the next question, how many moles of HCl are needed? So looking at our equation here, if we want to start with the HCl, we see that in the balanced chemical equation, 1 mole of iron reacts with 2 moles of HCl. So we are going to be using that mole ratio to calculate the moles of HCl. Okay, in the balanced equation, 1 mole of iron reacts with 2 moles of HCl. So that is what we are going to use to calculate the moles of HCl here. So we know that 1 mole of iron reacts with 2 moles of HCl, or 2 moles of HCl reacts with 1 mole of iron. So I'm stating this so that we know the conversion factor to use. The conversion factor that we are using here is the one where iron is at the bottom, so that the moles of iron is at the bottom, so that it will cancel out with the moles of iron here. So we have 4.21 times the conversion factor, which is 2 moles of HCl over 1 mole of iron. So we see that the moles of iron are going to cancel out, and we are left with moles of HCl. So if you multiply that out, you are going to have 8.42 moles of HCl. So that is what we have here. From the moles of iron, we have been able to determine the moles of HCl. Now, let's look at the next question. How many moles of iron 2 chloride are formed? So, for us to calculate the moles of iron 2 chloride that are formed, we are still going to use the moles of iron that we calculated first to determine that. So let's see the conversion factor that we'll be using for iron chloride. So if you look at the balanced equation, you will see that 1 mole of iron reacts with 1 mole of iron chloride. So we know that 1 mole of iron reacts with 1 mole of iron chloride, or 1 mole of iron chloride gives 1 mole of iron. So whichever of these ones, we are using the conversion factor where we will have moles of iron at the bottom to cancel out, and we have the moles of iron chloride that are left. So we are going to start with the 4.21 moles of iron that we already initially calculated to convert to moles of iron chloride. So 4.21 moles of iron times the conversion factor. So here we see that the moles of iron will cancel out the moles of iron, and we're left with moles of iron 2 chloride. So that gives us 4.21. So 1 mole of iron gives 1 mole of iron chloride. So 4.21 moles will give 4.21 moles. Now the next question is, how many grams of iron 2 chloride form? Now we know the moles of iron 2 chloride. To move from moles of iron 2 chloride to grams of iron 2 chloride, we need to use the molecular mass of iron 2 chloride. So the next thing that you have to do is you have to calculate the molecular mass of iron 2 chloride. And if you calculate that molecular mass, you will see that it is 126.75 grams per mole. So 126.75 grams per mole. Let's see the conversion factor that we are going to use. We have 126.75 grams per mole, or we have 1 mole to be equal to 126.75 grams. Here we have moles at the top, so we are using the conversion factor where our moles will be at the bottom, so we are going to use this one. So we are going to multiply by that conversion factor, and the moles of iron chloride cancels out the moles of iron chloride, and we are left with grams of iron 2 chloride. So we have look at what we've done. We started from 235 grams of iron, and we've been able to calculate the moles of iron. We've been able to calculate the moles of hydrochloric acid using the balanced chemical equation. We've been able to calculate the moles of iron 2 chloride using the balanced chemical equation, and from there we've calculated the grams of iron 2 chloride. As well, we could still calculate the moles of hydrogen from the moles of iron, or from the moles of hydrochloric acid, or from the moles of iron 2 chloride, since we have already calculated those. And from the moles, we will still move to the grams. Now, let's look at this question again. If 235 grams of the iron react in this way, so this is what we've already seen. Now, what you have to understand here is that we've used what is called stoichiometry. Okay? And stoichiometry means that we are using the amount of one material to predict the amount of another, which is based on the balanced chemical equation. Please take note. Balanced equation. If your equation is not balanced, you cannot successfully determine the grams or the moles of other reactants or products. Now, Let's look at another example here. When magnesium burns, it combines with oxygen to form magnesium oxide. If this reaction consumes 3.0 moles of oxygen, how many moles of magnesium oxide will form? Now, next question. How many grams of magnesium oxide will form? In the question, we've been given 3.0 moles of oxygen, and we are asked how many moles of magnesium oxide will form. So the first thing is that we have to look at the balanced chemical equation. From the balanced chemical equation, we'll be able to determine the moles of magnesium oxide that are formed. So let's see if our equation is balanced. On the left, we have 2 magnesium. To the right, we have 2 magnesium. On the left, we have 2 oxygens. To the right, we have 2 oxygens. So our equation is balanced. Now, let's convert from moles of oxygen to moles of magnesium, to moles of magnesium oxide. So for us to be able to convert from moles of oxygen to moles of magnesium oxide, we have to look at the balance equation, and we see that 1 mole of oxygen gives us 2 moles of magnesium oxide, or 2 moles magnesium oxide is 1 mole of oxygen. So we always start with the quantity that we've been given. We've been given 3.0 moles of oxygen. So we are going to use the conversion factor where moles of oxygen is at the bottom. So this is what we're going to use. So let's start. 3 moles of oxygen have been given to us. Now let's calculate. We are going to see. So we start out with the 3 moles of oxygen times the conversion factor. The conversion factor here is 2 moles of magnesium oxide are formed for every 1 mole of oxygen. So we are multiplying by that conversion factor. And we see that the moles of oxygen here will cancel out with the moles of oxygen, and we are left with moles of magnesium oxide. So you see, you multiply that 3.0 times 2. That gives you 6.0 moles of magnesium oxide. Now the next question is, how many grams of magnesium oxide will form? So for us to convert from moles of magnesium oxide to grams of magnesium oxide, we have to use the molar mass of magnesium oxide. And looking at the periodic table, you should be able to calculate the molar mass of magnesium oxide. So the molar mass of magnesium oxide will be 40.30 grams per mole. Now, this is the conversion factor, 40.30 grams per mole, or 1 mole of magnesium oxide is equivalent to 40.30 grams. So which of the conversion factors are we using? We want to convert 6.0 moles of magnesium oxide to grams. So we have to use the formula where the moles is at the bottom. So this is what we are going to use for this conversion. So let's see how we are going to do that. 6.0 moles of magnesium oxide times 40.30 grams over 1 mole of magnesium oxide. So the moles of magnesium oxide will cancel with moles of magnesium oxide, and we are left with grams of magnesium oxide. So we take 6 times 40.30, and that gives us 240 grams of magnesium oxide. Now, let's look at this other example. Sodium metal reacts violently with water. How many moles of hydrogen gas form if 11.0 grams of sodium react with water? Now, we've been given the grams of sodium, and we have been asked to calculate the moles of hydrogen. So the first thing that we have to do, analysis, we are going to convert grams of sodium to moles of sodium. Then from moles of sodium, we use the balanced equation to convert to moles of hydrogen. So how do we convert from grams of sodium to moles of sodium? We are going to use the molar mass of sodium to convert from grams of sodium to moles of sodium. So let's go ahead. The first thing, let's convert from grams of sodium to moles of sodium. So the molar mass of sodium is 22.99 grams per mole. So in this case, we are given 11.0 grams. So for the conversion factor, we will have grams at the bottom so that they will cancel out. Now we have 11.0 grams of sodium times the conversion factor. The conversion factor is 22.99 grams per mole. We will have the grams at the bottom in this case. So grams will be at the bottom, and you see that the grams of sodium will cancel out with grams of sodium, and we are left with moles of sodium. Now we have moles of sodium. With the moles of sodium, we are now going to use the balanced chemical equation to convert to moles of hydrogen. So let's look at the balanced equation. We see that 2 moles of sodium gives us 1 mole of hydrogen. So that is the conversion factor that we are going to use. 2 moles of sodium gives 1 mole hydrogen, or 1 mole hydrogen gives 2 moles sodium. Now we have obtained 0.478 moles of sodium. So which conversion factor are we going to use? The conversion factor that has sodium at the bottom, so that sodium will cancel out. So this is what we are going to use. Now, to convert from moles of sodium to moles of hydrogen, that is what we are going to use. 0.478 moles of sodium times that conversion factor, where we have 2 moles of sodium at the bottom, and the moles of sodium cancels out with moles of sodium, and we are left with moles of hydrogen. So you are going to divide 0.478 by 2, and that gives us 0.239 moles of hydrogen. So we see that we've been able to migrate from the grams of sodium to moles of hydrogen by passing through the moles of sodium. So this is very important. Now we have used 2 steps to solve out this problem. We could equally just write out everything just using one long equation. So if we have to do that, we will start by writing 11.0 grams of sodium times 1 mole of sodium over 22.99 grams of sodium. Alright, now we continue by multiplying by the mole ratio. The mole ratio here is 1 mole of hydrogen is giving us 2 moles of sodium. So all of those cancel out, and we are left with 1 mole. We are left with moles of hydrogen. So that gives us 0.239 moles. So what we did in 2 steps here, we are just using 1 step to bring it out. Now let's look at the summary of stoichiometry problems. We said if we know the moles of one of the species, for example hydrochloric acid, we can determine the moles of iron using the balanced chemical equation. We can determine the moles of iron chloride, and we can determine the moles of hydrogen. We saw how we can do that, and we've done that. Now, the conversion factors in stoichiometry problems, they are very important. Please take note of this. To convert from grams to moles, you have to use the molar mass. So this is the conversion factor. To convert from moles of A to moles of B, we have to use the coefficient in the balanced chemical equation. Very imperative. Now let's see how we move from moles of A to moles of B using the balanced equation. We are going to use their mole ratios. So if we have to convert from grams of A to grams of B, how do we solve that problem? We are going to move from grams of A to moles of A using the molar mass, and from moles of A to moles of B using the balanced equation and the mole ratios. And now from moles of B to grams of A using from moles of B to mass to the grams of B using the molar mass. So these are the formulas that you have to know. You need to know the path. This is called the conversion map. So make sure you know the conversion map. Now let's look at an example here. How we can move from grams of one reactant to the grams of the other. So when heated with a Bunsen burner, magnesium carbonate decomposes to magnesium oxide and carbon dioxide. As shown in this equation, if 5.24 grams of magnesium carbonate are heated in this manner, how many grams of magnesium oxide can be produced? So we have grams of magnesium carbonate, and we are now asked to calculate the grams of magnesium oxide. As the map shows, it shows that we are going to move from the grams of magnesium carbonate to moles of magnesium carbonate using the molar mass of magnesium carbonate, and from moles of magnesium carbonate to moles of magnesium oxide using the balanced equation, 1 mole reacts with 1 mole. So that is what we are going to use. And from the moles of the magnesium oxide that we obtain, we will then convert it to grams of magnesium oxide. So let's start. So that is the procedure. We are moving from grams of magnesium carbonate. We'll convert it first to moles of magnesium carbonate. Then from the moles of magnesium carbonate, we are going to convert it to moles of magnesium oxide. Then from the moles of magnesium oxide, we'll convert to the grams of magnesium oxide. So what have we been given? We've been given 5.24 grams of magnesium carbonate. So what we need here is the molecular mass of magnesium carbonate. So the conversion factor that we are using here will have the grams at the bottom and the moles at the top. So 5.24 grams of magnesium carbonate times the conversion factor, grams at the bottom and moles at the top, so that grams will cancel with grams. So here now at this level, we now have moles of magnesium carbonate. Now, to convert from moles of magnesium carbonate to moles of magnesium oxide, we are going to use the balanced equation and the mole ratios. So we see that 1 mole of magnesium carbonate gives 1 mole of magnesium oxide. So that is what we are going to use now. Then we see here now that the moles of magnesium carbonate cancels with the moles of magnesium carbonate, and we have now the moles of magnesium oxide. From the moles of magnesium oxide now, we have to convert to the grams of magnesium oxide using the molecular mass of magnesium oxide. And for the conversion factor, we are going to have the moles of magnesium oxide at the bottom and the grams at the top. So the conversion factor gives us that. So the moles will cancel out with the moles, and we are left with grams. So if you evaluate this, if you take 5.24 times 40.31 divided by 84.32, that is going to give you 2.51 grams of magnesium oxide. So we have successfully moved from grams of magnesium carbonate to grams of magnesium oxide using this map. So these are the strategies that you have to use. So if you are moving from grams and moles of one substance, the conversion factor that you have to use is the molar mass. Like if you are converting from grams of sodium chloride to moles of sodium chloride, you have to use the molar mass. That's the conversion factor. Now, if you are converting from moles and particles of one substance, if you have moles and particles, what you are going to use is the Avogadro's number. So you are using the Avogadro's number, which is 6.02 times 10 to the 23. Now, if you are converting from moles, of two different substances, you must use the balanced chemical equation. So it is from the balanced chemical equation that you will obtain the mole ratios. So this is the map that you have to follow. Here is the map of everything we've already stated. Same thing, make sure you master this map. So if you are converting from moles of A, for example, grams of A, to the particles of B, so you have to move from grams of A to moles of A. Then from the moles of A, you move to moles of B. Then from the moles of B, you move to the particles. Let's look at an example that have such a situation. Zinc metal reacts with aqueous copper 2 chloride as shown in this equation. So here's the balanced chemical equation. If 3.03 times 10 to the 21 atoms of zinc react, how many grams of zinc chloride will form. Show the sequence of conversions necessary, and then calculate the numerical answer. So let's do the analysis. We are moving from atoms of zinc to grams of zinc chloride. So if we have to move from atoms of zinc to grams of zinc chloride, we will have to first of all pass through the Avogadro to move from atoms of zinc to moles of zinc. Okay, that is the first thing. We use the Avogadro to pass from atoms of zinc to moles of zinc. Then we'll move from moles of zinc and use the balanced equation to move to moles of zinc chloride. Then from the moles of zinc chloride, we are going to use the molar mass of zinc chloride to convert to grams of zinc chloride. So we have analyzed the situation. So we are moving from atoms of zinc chloride to grams of zinc. We are moving from atoms of zinc to grams of zinc 2 chloride. And I've said we are going to pass through the Avogadro to move to the moles, and from the moles of zinc we are going to move to the moles of zinc chloride. From the moles of zinc chloride we move to the grams of zinc chloride. So that is the procedure. So that is what we are doing. We are moving from the particles here, particles of A, we will go to moles of A. From the moles of A, we will then move to the moles of B. And from the moles of B, we will then move to the grams. So that is what we are doing. We are moving from atoms of zinc to moles of zinc, from moles of zinc to moles of zinc chloride, and from moles of zinc chloride to grams of zinc chloride. Analysis done. Now let's do the numerical answer. So we have 3.03 times 10 to the 21 atoms of zinc. Now, for us to convert from atoms to moles, we are going to use the Avogadro's number. And we know that 1 mole is equivalent to, here we know that the atoms will be found at the bottom. So we are going to use the conversion. 1 mole is equivalent to 6.02 times 10 to the 23 atoms, since we are talking about atoms of zinc. So this is the conversion factor that we are going to use. So we multiply that by 1 mole of zinc to be equal to 6.02 times 10. So we see that here we have already, the atoms of zinc will cancel out and we are left with moles of zinc. Now, for us to convert from moles of zinc to moles of zinc chloride, we come to the balance equation. We see that 1 mole of zinc gives us 1 mole of zinc 2 chloride. So the conversion factor is 1 mole of zinc is equal to 1 mole of zinc chloride. So 1 mole of zinc will be at the bottom and 1 mole of zinc chloride will be at the top, so that we cancel out the moles of zinc. So that's our conversion factor. So that now the moles of zinc cancels out and we are left with moles of zinc chloride. So we are now going to move from the moles of zinc 2 chloride to grams of zinc 2 chloride. For us to do that, we have to use the molar mass of zinc 2 chloride. And if you calculate that molar mass, you are going to see that it's 136.28 grams. So for that conversion factor, the moles of zinc 2 chloride must be at the bottom so that they cancel out and we are left with grams. So if you evaluate this answer, it is going to give you 0.686 grams of zinc 2 chloride. So we've seen how we can move from moles to grams, from grams to grams, from grams to moles, from particles to atoms, from atoms. I mean, we've seen everything. So you need to master how to do these calculations. So here is still the map. Now, we are now moving to the concept of limiting reactants. So the mole concept in balanced equations. We are moving to the concept where it is called limiting reagents. What is a limiting reagent? When 2 or 3 reactants are put together to form a product, the reactant that finishes first is called the limiting reagent, which means that if that reactant runs out, the reaction stops. So the limiting reagent is the least, the one that is smallest. Now, we already saw that if we use this balanced equation, if we know the moles of HCl, we can calculate the moles of iron as well as the grams of iron. We can calculate the moles of iron chloride, and we can calculate the moles of hydrogen. So let's look at the calculations now with limiting reagents. Before we start this calculation, we are going to start with a very simple example here. We want to prepare a sandwich. And for us to prepare our sandwich, we need 2 slices of bread. We need 1 slice of turkey. We need 1 slice of cheese. So that is what makes a sandwich. So here, our sandwich consists of 2 slices of bread, 1 slice of cheese, and 1 slice of turkey. So that is what you need to prepare one sandwich. Now, what is going to limit the number of sandwiches that we prepare is what is going to run out first from the number of slices of bread that we have, the number of slices of turkey that we have, and the number of slices of cheese that we have. So let's look at this equation here. If you have 80 slices of bread, 18 slices of turkey, and 15 slices of cheese, how many turkey and cheese sandwiches can you make using this recipe? So we already know that for us to make one sandwich, we need 2 slices of bread, we need 1 slice of turkey, and we need 1 slice of cheese. So we have been given 80 slices of bread. So that is going to give us 40 sandwiches, because 2 bread slices give us 1 sandwich. So 80 of them will give us 80 divided by 2, which gives us 40 sandwiches. We also know that 1 slice of turkey is used to give us 1 sandwich, which means that our 18 slices of turkey will give us 18 sandwiches. We also know that 1 slice of cheese is used to give us 1 sandwich, which means that our 15 slices of cheese will give us 15 sandwiches. So now, what will limit the number of sandwiches that we can make? Here we have 15 for cheese, 18 for turkey, and 40 for the bread. It means that with the bread that we've been given, we can successfully make 40 sandwiches. With the turkey that we have, we can successfully make 18 sandwiches. And with the cheese that we have, we can only make 15 sandwiches. We see here that the limiting reagent is the cheese that can only give us 15. So cheese is what is called our limiting reagent, which is what runs out first. So once the cheese runs out, we cannot make any more sandwiches, because the recipe will not be what we need. So the cheese limits the amount of sandwiches that can be produced. Now let's look at it chemically now. So we are looking at it. Let's use cooking. Let's look at the kitchen in this case. In the kitchen, you see the gas here burning. This is methane reacting with oxygen to give us carbon dioxide and water. So what is the limiting reactant in this case? What is the limiting reagent? We see that we have here in this case, we have 2 moles of methane, and we have 1, 2, 3, 4, 5, 6 moles of oxygen. We have 2 moles of methane and 6 moles of oxygen. But in the balanced equation, you see that 1 mole of methane reacts with 2 moles of oxygen to give us 1 mole of carbon dioxide and 2 moles of water. So here, 1 mole of methane will react with 2 moles of oxygen, and the other 1 mole will react with the other 2 moles of oxygen. So oxygen is in excess. We have this one and this other one left. So the limiting reactant is methane. Oxygen is the excess reactant. That is why when you are cooking, immediately your gas, which is methane, once it runs out, the fire goes off. So methane is the limiting reagent and oxygen is called the excess reagent. Let's now look at another practical example. Potassium reacts violently with chlorine gas to produce potassium chloride, as shown in this equation. If 1.2 moles of potassium are combined with 15 moles of chlorine gas, how many moles of potassium chloride can form? Which reagent is the limiting reagent? So, the first thing that we have to do is we start by writing the balanced chemical equation. So here we see that 2 potassium atoms react with 2 chlorine atoms. So we have 2 moles of potassium reacting with 1 mole of chlorine to give us 2 moles of potassium chloride. That is a balanced equation. So what have we been given? We've been given 1.2 moles of potassium and 15 moles of chlorine. How many moles of potassium chloride can form? So we have to calculate which of these is limited. Now looking at the balanced equation, we see that 1.2 moles, so we have 2 moles of potassium reacting with 1 mole of chlorine. If we are given 1.2 moles of potassium and 15 moles of chlorine, it means that what will limit our reaction will be the potassium, because we have just 1.2 moles. So we have enough of potassium. We have enough potassium to produce the 1.2 moles of potassium chloride, and we have excess chlorine. So you actually calculate the moles of potassium chloride that will be produced using the balanced chemical equation, as we've already seen. So you are given 1.2 moles of potassium, you use the conversion factor in this balanced equation. 2 moles of potassium gives 2 moles of potassium chloride. So that gives you 1.2 moles of potassium chloride. Now, we also have to use the moles of chlorine that have been given and use the balanced equation to calculate the moles of potassium chloride. So we have 15 moles. Let's see. 15 moles of chlorine. We are now using the conversion factor. We have 1 mole of chlorine gives 2 moles of potassium chloride. So the conversion factor will have chlorine at the bottom. 1 mole of chlorine at the bottom, so that the moles of chlorine cancels out and we have moles of potassium chloride. So we see here that the 15 moles of chlorine are going to give us 30 moles of potassium chloride, and the 1.2 moles of potassium are going to give us 1.2 moles of potassium chloride. So the limiting reactant here is what gives the smallest number of moles of product. So our potassium here is the limiting reactant because it produces the smallest amount of potassium chloride. Just like we were using cheese, bread, and turkey, the cheese was the one that gave the smallest amount of the sandwiches. So cheese was the limiting reactant. So here, the potassium is giving the smallest amount of potassium chloride, and so potassium is the limiting reactant. Now, the chlorine that is left is called the excess reactant. So we will still have more of the chlorine that is left after the reaction has gone to completion. So this is how we calculate limiting reactants. Now, let's look at this one more example before we move to another method. So uranium reacts with fluorine gas according to this equation. If 30 moles of uranium combine with 75 moles of fluorine, how many moles of uranium hexafluoride will form? Now, we have uh, 30 moles of uranium combining with 75 moles of fluorine. So if you just look at it in this case, that 30 moles of uranium and 75 moles of fluorine, you think that 75 moles of fluorine are much and 30 moles of uranium are small, you will fail. Let me show you why. Let's go ahead with the calculation. Now, let's see how we can convert from moles of uranium to moles of uranium fluoride. So, we have 30 moles of uranium. We see that in the balanced equation, 1 mole of uranium gives 1 mole of uranium fluoride. So that is the conversion factor that we're going to use. So let's see, that is going to be times 1 mole is to 1 mole, right? So that gives us the 30 moles of uranium fluoride. Okay, so the 30 moles of uranium gives us 30 moles of uranium fluoride. Now let's see how many moles the 75 moles of fluorine will give us for uranium fluoride. In the balanced equation, 3 moles of fluorine gives us 1 mole of uranium fluoride. So the conversion factor is 3 moles of fluorine is equal to 1 mole of uranium fluoride. And for the conversion factor, the fluorine will be at the bottom so that it can cancel out. So we'll have 1 mole of uranium fluoride at the top and 3 moles of fluorine at the bottom. So we are going to multiply 75 times 1 mole of uranium fluoride by 3 moles of fluorine at the bottom. So you see that you have 25 moles of uranium fluoride. So which of these gives us the smallest amount of product? We see that the 75 moles of uranium fluoride, of fluorine, sorry. So fluorine is actually what is giving us the smallest amount of product. Fluorine gives us 25 moles of uranium fluoride and uranium gives us 30 moles of uranium fluoride. So if you were looking at just the 30 moles of uranium and 75 moles of fluorine, you would think that fluorine is the excess. So you must calculate it. You don't just assume. So fluorine is the limiting reactant and uranium is the excess reactant. So we are going to use another method here that is called the ice method. Okay, we are still using the bread, the slices of bread, the turkey and the cheese. For this method, we are going to use the ice method. In a minute, I will tell you what ice is about. I stands for initial, C stands for change, and E stands for N. So if you make all of the sandwiches, what will be left over? So we are now calculating the excess reactant. In this case now we are calculating what will be left, the excess. So we are using the ice method to calculate that. So I stands for initial. So initially, how many slices of bread did we have? We had 80 slices of bread. Okay. We had 18 slices of turkey. So that is what we had initially. We had 15 slices of cheese and we never had no sandwich. So initially there was 0 sandwich. Now at the change, C stands for change. At the change, we see that we used all the slices of cheese, the 15 of them, to form 15 sandwiches. And we also used 15 slices of turkey. So what is being consumed is given a minus sign, and what is being formed is given a positive sign. So reactants are always consumed. So you will see for the change, reactants are always going to be negative. So for the slices of bread, we used 30 slices of bread. So at the change, we see that we used 30 slices of bread, 15 slices of turkey, and 15 slices of cheese. So when we used all of this, how many sandwiches did we form? We formed 15. Because it is a formation, it is going to be positive. So we formed plus 15 sandwiches. Now, at the end, what is left? So at the end, what is left, we are just going to subtract what has been used from what we initially had. So we see that for the slices of bread, we are going to be left with, if you subtract 30 from 80, you are going to be left with 50. So for the cheese, we'll have 0. For the turkey, we'll have 3. And for the bread, we'll have 50. And that is what we've obtained. So we successfully formed 15 sandwiches. So this is the ICE method here, the initial, change, and the end. So initially, you state out what you have. At the change, for the reactant, you subtract what has reacted. And for the product, it is positive because it is being formed. And at the end, you actually subtract what has reacted from what you initially had. Now, let's use the ICE method to solve this problem here. If 15 moles of hydrochloric acid and 20 moles of sodium hydroxide are combined, how many moles of each species will be present after the reaction is complete? So, this is the same like they could still ask you what is the limiting reactant and how much of the excess reactant is left. So that's what this question is asking. So if we are using the ICE method, let's state out what we have. Initially, we have 15 moles of hydrochloric acid and we have 20 moles of sodium hydroxide. We don't have any sodium chloride or water, so we have 0 moles of each. Now, looking at the balanced chemical equation, we see that 1 mole of hydrochloric acid reacts with 1 mole of sodium chloride to form 1 mole. It reacts with 1 mole of sodium hydroxide, to form 1 mole of sodium chloride and 1 mole of water. So, for the change, all the 15 moles of hydrochloric acid will react. This will react with 15 moles of sodium chloride as well because they react in the ratio 1:1. And that will form 15 moles of sodium chloride plus 15 moles of water. Now at the end, what is left? So let's draw our line. We know that we've used all our hydrochloric acid. All that we have left is sodium hydroxide. So let's see. We have 0 mole of hydrochloric acid left. We have 5 moles of sodium hydroxide left. And we formed 15 moles of sodium chloride and 15 moles of water. So what is left, according to the question, how many moles of each species will be present after the reaction is complete? After the reaction is complete, we'll have 0 mole of hydrochloric acid, 5 moles of sodium hydroxide, 15 moles of sodium chloride, and 15 moles of water. So let's see the summary of limiting reactants. We've said the limiting reactant is the reactant that is completely consumed and it limits the amount of the product that is formed. So the reagent that forms the least amount of product is the limiting reagent. And for the excess reagent, we say it is not completely consumed. It is a reagent that will be left over after the reaction is complete. So the ICE method can be used to determine the amount of all reactants and product present after a reaction has taken place. So now let's look at what is called the percent yield. Percent yield and theoretical yield. Percent yield and theoretical yield is what chemists use to determine the success of a chemical reaction. If they were carrying out a particular reaction, they are going to use percent yield to determine how successful that reaction actually went. If the yield is very high, close to 100%, it means that the reaction was well carried out. Now, the theoretical yield is the amount of product that can form based on the balanced equation. So all what we've been calculating, the amount of product formed, that is the theoretical yield. So when a reaction is carried out, what is obtained is the actual yield. And the actual yield is always less than the theoretical yield because some of the product will be stored in the equipment that you are using. Some of the product will be loose when you are trying to purify your product. So the percent yield is the percent of the theoretical yield that was obtained. So how do we calculate percent yield? Percent yield is given by the actual yield over the theoretical yield times 100. Now, why is the actual yield so low? Let's say you wanted to make a cake, and here you have chocolate. Here the material sticks to the walls of the container, and there are unwanted side reactions. So you cannot get all of the chocolate out of this bowl. Okay, so the cake that you will form, the product, the yield will be actually less than the theoretical yield that has been calculated. So a chemist, let's see this example. A chemist runs a reaction in which the theoretical yield is 240 grams. However, he is only able to isolate 180 grams. What is the percent yield of this reaction? So this is the theoretical yield. Theoretically, it shows that he will obtain 240, but actually he obtained only 180 grams. So what is the percent yield? So the percent yield is the actual yield, which is 180, over the theoretical yield, which is 240 times 100%. So that gives us 180 divided by 240 times 100. That gives us 75%. So he was 75% effective. Now let's look at this last reaction. Sulfur hexafluoride is widely used in the power industry. It is produced through this reaction, sulfur plus 1 mole of sulfur plus 3 moles of fluorine to give sulfur hexafluoride. A manufacturer reacts 120 kilograms of sulfur with excess fluorine gas. What mass of sulfur hexafluoride is theoretically possible for this conversion? After the reaction is complete, the manufacturer isolates 480.2 kilograms of sulfur hexafluoride. What was the percent yield of this process? Now, let me show you what is going on. First, we have to look at the balanced chemical equation. With the balanced chemical equation, we will be able to calculate the theoretical yield. Okay, and now, after he carries out the reaction, he actually obtains a 480.2 kilograms. So this is the actual yield. Now let's calculate the yield of sulfur hexafluoride using the 120 kilograms of sulfur. We already know that fluorine was excess, so sulfur is the limiting reactant. So we are using the 120 kilograms of sulfur to calculate the amount of sulfur hexafluoride that will be formed. That is the theoretical yield. So first thing here is that we are going to convert the 120 kilograms to grams. Remember the molecular formula. The molecular formula or the molar mass is given in terms of grams per mole, not kilograms per mole. So we have 120.0 kilograms. We now have to convert it to grams. What is the conversion factor? We know that there are 1,000 grams in 1 kilogram. So 1,000 will be at the top. 1,000 grams in 1 kilogram. So you see that kilograms will cancel here, and we are left with grams. So we are going to have 120,000 grams. So that is the value that we have. So we are moving from grams of sulfur to grams of sulfur hexafluoride. So to do that, we have to move from grams of sulfur to moles of sulfur using the molar mass of sulfur, and then we move from moles of sulfur to moles of sulfur hexafluoride using the balanced equation, and then from the moles of sulfur hexafluoride to the grams of sulfur hexafluoride using the molar mass. So that is the procedure that we are using here. Now let's start with the 120 kilograms. We have to first convert it to grams, then multiply by the molar mass. Use and multiply by that conversion to get the number of moles. So we have 120,000 grams of sulfur times the conversion factor. So we are going to have moles at the top and grams at the bottom. So we'll have 1 mole of sulfur at the top, which is equivalent to 32.06 grams. So that we see that grams of sulfur will cancel here, and we are left with moles of sulfur. So for moles of sulfur now, we are going to convert to moles of sulfur hexafluoride using the balanced equation. So we see that 1 mole of sulfur gives 1 mole of sulfur hexafluoride. So the molar ratio is 1:1. So we multiply that by that ratio. Now, we have the moles of sulfur hexafluoride. So moles of sulfur cancel out. Then what we are going to do now, we are then going to convert the moles of sulfur hexafluoride to grams of sulfur hexafluoride. So how do we do that? We multiply this by the molar mass of sulfur hexafluoride, and the grams of sulfur hexafluoride will be at the top and the mole will be at the bottom for the moles to cancel out. So we cancel out the mole and we are left with grams of sulfur hexafluoride. Now, what numerical value does that give us? That gives us 546,700 grams of sulfur hexafluoride. That is the theoretical yield. Okay, so that is the theoretical yield. But what was the actual yield? The actual yield was 480.2 kilograms. Now, what we have to do, we also have to convert 480.2 kilograms to grams. So we are going to multiply that by the conversion factor, 1000 grams over 1 kilogram. So we see the kilograms here will cancel, and we have the answer there in grams. So now, to calculate the percent yield, we are going to say is the actual yield divided by the theoretical yield times 100. So either ways, either you convert this to grams and work it out, or you convert the answer we have obtained here to kilograms and work it out. That will still give you the same answer. So if we convert what we've obtained here to kilograms, we have 546.7 kilograms. Now the percent yield will be equal to the actual yield, which is equal to 480.2 kilograms divided by 546 times 100. That gives us 87.84%.